Imagine this. A patient walks into a hospital after weeks of headaches and blurred vision. The doctor orders an MRI, and within minutes, the scan reveals a tumor in the brain. In that critical moment, every second counts. But identifying and analyzing a tumor isn't always straightforward. It requires precision and expertise. This is where artificial intelligence steps in, transforming healthcare by making tumor detection faster, more accurate, and more accessible. At the heart of this transformation is the BraTS Dataset, which stands for Brain Tumor Segmentation, a collection of expertly labeled MRI scans that fuels AI models for brain tumor segmentation. In this video, we'll dive into why BraTS is a game changer for medical imaging. So, why does BraTS matter? Brain tumors are some of the most dangerous problems, and they are hard to spot. Doctors need tools that can help them detect tumors quickly and plan treatments. That's exactly what BraTS is for. It's a collection of brain MRI scans used to train AI to identify and study tumors, which save doctors time and gives patients a better chance of recovery. To truly understand the brain tumor, we need to think like a detective solving a case. Each MRI modality is like a crucial clue that contributes to cracking the mystery. Together, these clues form the complete picture, allowing us to uncover the truth. Let us dive into the different modalities of our BraTS, starting with our baseline view, the T1 weighted MRI, which shows the brain's overall structure, helping doctors see its anatomy clearly. When a contrast agent is injected is when we get to the interesting part, the T1 post-contrast, that highlights active tumor regions, making them stand out against the rest of the brain, a crucial contribution for identifying the tumor's active and aggressive areas. Switching focus to fluid dynamics, T2 weighted MRI identifies areas of fluid accumulation, such as edema or cysts. This is particularly useful for recognizing swelling caused by the tumor, helping to gauge its indirect effects. Building on T2, T2 FLAIR, which stands for Fluid Attenuated Inversion Recovery, takes it a step further by filtering out normal fluid signals like cerebrospinal fluid so we can focus on edema or swelling around the tumor, which gives a clearer picture of the tumor's impact on the surrounding tissues. Finally, the dataset provides segmentation mask color coded overlays that separate different tumor regions. The enhancing tumor core, necrotic core, and edema, these annotations are like a map guiding AI to precisely locate and classify tumor areas. Each modality adds a layer of understanding. By combining T1, T1JT, T2, and FLAIR, we provide AI with a 360-degree view of the tumor. Think of these modalities like a layer of an onion. Each one adds a new perspective, giving AI a complete picture of the tumor's size, shape, and surroundings. This multimodal approach is what makes BraTS so effective for training AI models. Let's take a closer look at the BraTS dataset. From the start, the dataset files are stored in the neuroimaging format, specifically NIfTY files. This format is widely used in the medical imaging community because it allows for storing 3D data like MRI volumes efficiently. When we loaded the dataset's training metadata file in Python, we found several important columns that help us navigate this data. Each row in the metadata represents a slice of an MRI scan, and the columns provide detailed information about that slice. Slice path, the file path of the MRI image slice. Volume, the ID of the patient's MRI volume. Slice, a specific slice number within the volume. And target indicates if the slice contains a tumor region. Other columns like label 0 pixel count, label 1 pixel count, and background ratio describe how many pixels in the slice belong to specific tumor regions or the background. Now, why does this matter? These columns serve as the building blocks for training AI models. For example, the target column helps AI learn which slices have tumors, while pixel counts help it focus on specific regions. What makes BraTS unique is the precision of its annotations. Each MRI scan is manually labeled by 1 to 4 radiologists and reviewed by experienced neuroradiologists. The annotations define critical regions like the enhancing tumor core, where active tumor growth occurs, the peritumoral edema or swelling around the tumor, the necrotic core, where tumor cells have died. These labels guide us to differentiate between healthy brain tissue and tumor areas. Make sure you have a Kaggle account, as you'll need it to download the files. Once you're on the page, click the download button at the top right. The dataset is quite large, around 42.8 gigabytes, so ensure you have enough storage and a stable internet connection. It is organized into 2 main directories, one for training data, BraTS 2020 training data, and another for validation data, BraTS 2020 validation data. The training data folder contains 369 directories and 2 files. After downloading some nifty files, let me show you their visualization to give you an idea of what they look like. For each file, I extracted the middle slice of the 3D image, which represents a key cross-section of the brain. These visualizations highlight the unique characteristics of each modality, helping us understand the data better. If you're interested in coding and want to explore more, you can find several notebooks on Kaggle that use this dataset. Here's an example. This notebook demonstrates a 3D brain tumor segmentation pipeline using the UNet architecture. It processes the BraTS dataset, trains a model to classify gliomas, and achieves a remarkable 99% accuracy. Interestingly, the BraTS dataset is also central to the annual BraTS Challenge, held at the Center for Biomedical Image Computing and Analytics conference that has been running since 2012. It gives researchers a chance to test and improve their methods for understanding brain scans. For BraTS 2024, the challenge has grown with a bigger dataset of about 4,500 cases. This year's tasks focus on different kinds of problems, like post-treatment glioma with a new dataset, the underserved sub-Saharan African brain glioma patient population, radiotherapy meningioma with a new dataset, brain metastasis, pediatric brain tumor patients, global and local missing data, useful augmentation techniques, and pathology with a new dataset. The BraTS challenge isn't just about technology, it's about solving real problems. In some parts of the world, like sub-Saharan Africa, there are very few doctors and patients often wait a long time for diagnosis and treatments. AI tools like the 3D UNet model can help doctors work faster and more accurately. This means earlier detection for brain tumors and better chances for patients. The strength of BraTS lies in its diversity and quality. The dataset includes MRI scans collected from 19 institutions around the world, making it highly representative of real-world clinical scenarios. As you mentioned before, it's annotated by radiologists, ensuring that the data is both accurate and reliable. This diversity allows AI models trained on BraTS to perform well across various clinical settings, not just the environments they were trained in. A 2023 study by Mustafa and colleagues highlights the incredible potential of BraTS. Using 335 MRI images from the dataset, they trained a pre-trained convolutional neural network to detect and segment brain tumors. The result? An impressive 98% accuracy, an indication of the dataset's quality and its role in advancing tools for diagnosis. Of course, no dataset is perfect. BraTS focuses primarily on gliomas, meaning it may not generalize to other types of brain tumors. Additionally, variations in MRI machine settings and protocols can lead to inconsistencies in the scans. This can make it harder for AI to work perfectly everywhere. The BraTS Dataset is not just a dataset, it's a tool for saving lives. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more deep dives into fantastic datasets and where to find them channel.